In front of you, you'll see this document here, Understanding the Napatech World, which gives a few quick introductions to some of the terms that you'll hear during today, like FPGA and servers and networks and all of the things that you will be talking about during the day. The next part of the presentation here, I'm just going to go through some of those concepts, and particularly what is reconfigurable computing, which you're going to hear a lot about today, and what is an FPGA, and how does it actually work, and how is it different. So please stop me at any time during this presentation if there's something you just want to hear, or if you didn't understand something I'm presenting. The idea here is that you get a feeling for what these things are, so that as we go through the day and you hear about the market opportunities and Xilinx and Intel and all the things they're presenting, that you have some grounding in what they're talking about. Okay? So I want to start off by trying to explain what Napatech does, and to do that I just wanted to use an analogy that we might all understand, and just normal traffic. So if you imagine a city like Oslo, basically there's a lot of traffic coming into Oslo, all different types, and if you had to manage that, then basically what would you do? Well, one of the first things you would do is you would set up a lot of different sensors and different cameras around the place, so that you could see what's happening in all places at all times, right? That would help you to make sure that traffic reaches its destination efficiently, so there's no traffic jams, and that you're using the traffic lights and other things to steer traffic in the right directions. And of course, if anything happens, you can assure the safety and report any incidents quickly and get the police and the ambulances to where they need to be as quickly as possible. So this is what you would do if it's a normal traffic situation. It's not much different to the world that we live in. For us, it's not a city that we're going to, it's these big hyperscale cloud data centers, and it's not roads that we're on, it's connections in a network, which looks something like this. So if you imagine that you have these hyperscale cloud service providers as your big cities, and they're all connected by these roads to us, the users, with our devices, smartphones, etc. We're using all these different services that are being supported in the hyperscale cloud service data centers. But it's the same job that has to be done. We want to make sure that we can see what's happening in all places at all times, so that we can make sure that traffic is reaching its destination efficiently. But we also want to make sure that we're doing what we're calling switching in there, to make sure that that data is actually getting to where it needs to be at the right time. And also we want to ensure the safety and report any incidents that are happening in the network as well. So these are all the things that go around making sure that we're all getting our services the way we want them, and that they're safe. So it's about delivering things in a smoothly, efficiently, and safely in these networks. That's basically the idea behind what we're doing, the technologies that we're making, and the solutions that we're bringing out. So any questions on that? Does that make sense? So have that in mind when you're thinking about the things that Napatech is doing. Now this is a picture you might have seen before, which is another way of telling that story, where again you see the hyperscale cloud service providers in the middle. They're the ones who are providing all these services that we rely on every day. We're connecting to those with our smartphones, our tablets, and our laptops, and moving forward it'll be 5G, the 5th generation of mobile technology that we'll be using for that. And of course 5G is not just for giving us higher data speeds, it's also for enabling some of these more advanced services for autonomous smart cars, for having Internet of Things, smart sensors all over the place that we'll be collecting data from, and also smart city solutions that are going to be there. So it's becoming a much bigger world. There's going to be billions of connections, millions of services out there, and they're all going to be anchored in these hyperscale cloud service data centers. Now hyperscale just means it's huge, and this is the way these data centers are being built. And our friends from Xilinx and Intel are absolutely experts in this area, so if you're curious about that, please ask them those questions when it's their presentations. But basically what they are is very large buildings with, I'm saying thousands here, but it's actually even hundreds of thousands of standard servers that are just interconnected, and where you can host all of these different services here. Now what makes this possible and what makes it really efficient is the fact that the standard server is like a building block. It's a common computing platform that any of the services can run on. And what makes that great is that if you want to support more connections or more services, you simply add more of these common compute platforms, just like bricks, right? So that's what enabled hyperscale to become what it is today. And the standard computing platform or the standard server is basically what is used in these data centers today. And that's no different. If you hear standard server, just think of your PC at home. It's the very same thing. It's just at a more industrial scale. So it's got the same things inside. It's got a CPU for running the programs and processing the data. And it's got a network interface card, which is for connecting to the network and getting data in and out, right? It's as simple as that. The issue has been, though, that of late, the processing power of these solutions are struggling. The reason for this is that we've been following something called Moore's Law, and it's been enabling us to keep up with the growth. Now, Moore's Law states that you can double the capacity or the performance of these systems every 18 months, and it's something that came from Intel. The need is continuously rising because we've got more users coming onto these services, more connections, more data being driven every day. So we really rely on these platforms increasing their performance at that rate, doubling their performance every 18 months. We simply rely on that. But what's happening is that performance is facing some physical challenges because the way you get the CPU to be more performant is making the geometries on it smaller and smaller and smaller. So you start to face some physics problems here, some real problems about how many transistors you can get onto a chip and how small you can make the connections and how narrow they can be. And we're down in the nanometers here, so it's really small. And the power efficiency of these things and how you can get out of it. So basically the conclusion is that is reaching its limits of what you can do. So we're searching around for what is the next thing that we can do. How can we close this performance gap that we have between what we need and what we're able to get from the standard computing platform? And the answer is to add FPGAs, field programmable gate arrays, to the solution. So it's basically these same servers, these same standard computing platforms, we add in this technology called FPGA as a complement. And the reason why that's a good idea is because the FPGA is brilliant at scaling and doing certain tasks very well, very efficiently, much faster than you can do in a CPU. So combining the two of them together allows you to have a much more efficient system where you can balance who does what. You can get the CPU doing what it's doing best and the FPGA doing what it's doing best, and the overall system improves its performance. So this is what we're going to be talking about a lot today, and this is what we call a reconfigurable computing platform. Now, so what is an FPGA? You're going to be hearing this a lot, a field programmable gate array, a very technical term, but what is it? Well, it's a chip just like a CPU. And what is inside of it is basically an array of blocks, if you like, building bricks, which are either processing data or they're storing data. And you can basically combine these any way you want to do a specific task. And the way you define them is using software. So you basically make a software file to say that connects to that and that connects to that, and basically build a process up. And once you've done that, the process is in the chip and it's very deterministic. So when you run data through it, it goes through those steps, goes through those blocks, and it's very predictable what you're going to get. It's guaranteed, right? And the other thing you can do with it is you can scale those, so you can have multiple of these processes running at the same time. So by doing that, you can actually run some tasks on this, and you can process a lot of data in parallel and have a very deterministic performance for that. So this makes the FPGA ideal for some of those very heavy computational loads that you have to do in a data center. So right, from that it could be very difficult to understand what exactly is that compared to a CPU. And so I just want to give a couple of slides here to give you an idea of what does it do and why is it so great. So it's a very simple analogy. It's a kind of a fast food service analogy, if you like, right? So what I'm comparing here is your CPU, which is the processing unit in the actual server that we have today, with the FPGA chip that will be sitting beside it. So what is it that's different about these two? Well, one way of looking at it is to think about your local grill bar in the corner, right? You get a lot of customers coming in there, and some will be ordering burgers, some will be ordering pizzas, some will be ordering sandwiches. And the expectation is the guy behind the bar, he knows the process for making a burger. There's certain steps through that. He knows the process for making a pizza, etc. but he's expected to take all these orders at once and multitask between them. And he can do that. I mean, while he's making the patty for the burger, he can be getting the lettuce for the sandwich, and he can be baking the bread for the pizza. So he can actually cut this up and satisfy everyone at the same time. Now, if you want to get bigger and faster with that, either he gets faster or he gets a buddy in who's just like him, and they're both doing the same thing. But the idea is they both know how to service everybody. So that's what a CPU does. It's a multitasker. But if you look at an FPGA, it's like walking into a McDonald's or a Domino's or a Subway, right? They're specialized at doing that process of making a burger or making a pizza or making a sandwich. And they'll have multiple people on stations that are all just set to do one thing, right? And everybody's order will go through the same process. So I'm going to get the patty, I'm going to put the bread on, I'm going to put the lettuce on, etc. And if you want to scale that, you just make more stations, right? So in that way, you can get a lot more done. It's a lot more efficient than if you're going to your local grill bar. And you're going to get a predictable quality every time. So that's the difference between the CPU and the FPGA. The multitasker, which is great at doing lots of things, besides the FPGA, which can make a process and be excellent at running that process and scaling it. Now, to bring that down to something in the real world that we're handling, you can look at it this way: as a CPU on a typical server would have to handle different tasks. It could be hosting a website, for example. It could be processing a financial transaction. But if something big comes in that needs to be processed, like encrypting data, which is a very computationally heavy activity, then basically the other things are just going to have to wait while it's working its way through that, right? And that means it gets quite inefficient because these guys can't get done what they need to get done. So you'll start to see these fluctuations in performance and latency, things getting delayed through the system, and that's not what you want. So if you combine it with the FPGA, you can take that very heavy load and you can offload it to the FPGA, and the FPGA can build that process for encrypting the data and do it really efficiently and do it at a very big scale, right? So this is the idea behind combining the CPU and FPGA. By making this combination, you ensure that the right workload is being sent to the right place, and from an entirety, the system is running smoothly and efficiently. So that's the whole idea of combining these two technologies. Right,
so why wouldn't you throw in a pizza chip and a burger chip in the system? Like Broadcom or Melon?
Yeah, I mean, you can do that. I mean, certainly you have solutions there. If you think all I'm ever going to be doing is encrypting data, then yeah, you can make a specialized chip for that and you can do it. But I think what we're beginning, and we've been doing that for years, there's been specialized chips for doing certain functions for many years. I think the difference that we're facing now, though, is that with all these new technologies that are coming out with 5G and IoT and new ideas and new solutions and a lot of open source involvement, what we're finding is that the new technologies are coming so fast and the new solutions are changing so often that the time it takes to make a chip and make something that's of that kind is just too long. So one of the reasons why an FPGA is great is because you can actually change it using software and change it really fast. So one day you can have it doing encryption of data, but by just making a software file update, you can get it to do compression of data, or you could do transcoding of videos, or I think that's kind of versatility is what really is interesting for the data centers and the community at large. I mean, think of a data center. A data center doesn't actually, it doesn't have its own products. It's actually hosting stuff for other people. Right, so I don't know what all these servers are going to be used for, but I'm going to make sure that everything can run on it. By having an FPGA in all these different servers, it now has the flexibility and versatility to handle anything. So, your particular process needs to encrypt data, no problem. We can actually offload that to an FPGA software image, right? That is made for that. It's like, oh, you want to compress data now as part of your process? No problem. We can update the FPGA so that it does that instead. So this is where the reconfigurability of these solutions really is exciting, because you've never been able to do this before, right? Right, and Intel and Xilinx are actually putting all of the frameworks in place, the software and everything to make this happen and make it easy for these data centers to do it. And they'll be talking about that a little bit more later on. Great question. Helped me to cover a point I didn't cover before. Yes.
Yes. envisage in hyperscale data centers today to combine CPU and FPGA technologies? And
Yeah.
how do you see that development going forward?
Yeah, so we certainly have some pioneers in this space. One of the biggest ones is Microsoft Azure. So they've actually moved a lot of the processing of their data to FPGAs in their data center. Actually using a format similar to what we're talking about today, the SmartNIC with an FPGA on board going into a standard server. They've actually adopted that and they're using it throughout their data centers to do Bing, Microsoft 365, all of these different things are now running on FPGAs. So they're the pioneers of this space. But you'll see later on that there's others like Alibaba and Amazon and others who are actually adopting this for FPGA as a service. So it's emerging, but there's definitely a lot of interest in the community about how we can use FPGAs to start accelerating these different workloads and the versatility of the FPGA. I think Intel and Xilinx could tell you a lot more about that later on. Okay. So I just want to wrap up, last slide here, just to give you an idea of where this is going at the moment. And one of the things I think is quite interesting about this is that we're coming with a new approach here which offers a lot of benefits, but we're not asking data centers to completely rip out what they've got and put in something new. One of the first steps, the first options you have for turning a standard computing platform into a reconfigurable computing platform is simply to put in that SmartNIC FPGA, as we were talking about before. Right, so it's as simple as taking the NIC that's in that server and replacing it with a SmartNIC FPGA. And now you've got a reconfigurable computing platform. And that's exactly what Microsoft Azure did. And I mean, they have literally millions of servers. So it was it's a big calculation that you have to make. But the versatility it provided them was priceless. So that's one option. But as we move forward, I think Intel and Xilinx could talk about this more about other options. But as we move forward, you're going to see the FPGA technology starting to get embedded in some of the CPUs. So we've already explored an Intel solution, for, as a matter of fact, where you combine the CPU and the FPGA in one chip package and see what you can do there. And you're also going to see them turning up on the motherboards in the servers. So they're going to be an integrated part of the servers. So you don't have to have a SmartNIC FPGA, but actually you probably would like to, because what you'll find is the sizes of these FPGAs might be a little different, and then the ability to be able to split up your work so it's closer to the network or closer to the CPU is what you're going to see going forward. So, so a lot of different options are coming, and there's certainly a trend towards it. So we're seeing the start today, SmartNIC FPGAs, turning standard computing platforms into reconfigurable computing platforms. But as we go forward, we're going to see servers coming out with this stuff embedded, being native reconfigurable computing platforms. Yes?
Could you maybe explain how you would kind of attack these three options and how they would affect Napatech?
Yes, thank you very much. You'll hear more about this as we go through the day. So, we've always been a hardware and software company because, as you know, I just told you the FPGA needs to be programmed using software, and there's a whole complex of software around that. And we've actually built a name for ourselves as being one of the best in the world at actually making solutions around that with software and hardware working together. So the initial opportunity for us, obviously, is the SmartNIC FPGA hardware. We think there'll be a need for these SmartNICs for many, many years. And there's a software that goes with that, obviously. So there's a hardware and software opportunity there. But as we move into these new reconfigurable servers, we now have an extension of that. So we believe that there will always be a need for SmartNIC FPGAs, but now we can actually put our software onto the FPGA running on the CPU, or we can put the software onto the motherboard FPGA. So it actually extends our reach. Where today it's all about getting a SmartNIC in there. In the future, it'll be SmartNICs, but also running on all the other parts. So we've become more integral to how the actual system works. So it's a fantastic opportunity for us.
But if you look at these hyperscale players, do you envision how large do you envision the penetration of your SmartNICs in these basic servers in the data centers?
Yeah. I don't know if I can forecast for you anything here, but it'll differ, I think, from player to player at this point. I think Intel and Xilinx can give you more insight into what they're experiencing out there now with what they're doing. And we're having very different conversations. Some want to deploy them everywhere from the beginning, and we think that is the end goal because you want to have that versatility in all of your servers. Others will take it on a solution by solution basis. So you're probably looking at things in the beginning which are going to be very solution focused. I have an issue here I'd like to get solved, and I'd like to solve it using reconfigurable computing platforms. So I think that's the first steps, and it's definitely driving many of the engagements we have now. But moving forward, as the industry gets more aware and comfortable with this kind of approach, you'll start to see people preparing for this and starting to actually deploy on a wide scale to be prepared for the future solutions that they need to use these technologies.